Hello, and thank you for joining me today for a discussion on chemical reactions and chemical equilibrium. At the end of today's lesson, you should be able to explain how activation energy impacts chemical reaction rates and chemical reactions in general. You'll be able to differentiate between endothermic and exothermic reactions. You'll be able to describe how a reversible reaction works. You'll be able to define Le Chatelier's principle and apply it to a given scenario. So let's get started. To start with, in order for a chemical reaction to happen, reactants have to come in contact with each other. And two things have to come together in order for something to react. Along with that, they need this activation energy, which is the energy required to break the bonds the reactants have and allow them to react. So for example, we're going to look at in this slide, we're going to look at the reaction that produces ammonia. So N2 plus H2 produces NH3. So in this case, we got to break these bonds between the nitrogen molecules and the hydrogen molecules in order to form this compound over here. And so it would actually be a 2 and a 3, and then we're good. Okay? And so this is activation energy. This is the energy that's required to break these bonds here in order to form these bonds over here. So we're going to look at that today. To go with that, you have a couple different types of reactions. We have endothermic and we have exothermic. So endothermic, endo meaning into, is bringing energy in. So energy must be absorbed in these reactions. So the energy of your products is going to be greater than that of your reactants. So energy is absorbed during this reaction. Exothermic, exo being exit. Energy of the products is less than energy of your reactants. So energy is released. Energy exits the system, goes to the surroundings. And then these two both work. In both situations, we have what's called a rate of reaction. So rate of reaction is the amount of reactant used up or amount of product produced in a certain amount of time. So this is the simple way is to think of your change in concentration divided by your change in time equals rate of reaction. Okay, so that is rate of reaction, and those are endothermic and exothermic reactions there. This graph was on the slide 2 slides ago. This is showing you activation energy in regards to the different types of reactions. So on the left, you have your energy. So this is potential energy of the reactants, of the system. So the reactants are here, which is this line. So they have this much energy. My products are down here. You will notice that my products have less energy than my reactants, which means that they lost some, which means this is an exothermic reaction. Okay, but instead of just going straight from reactants to products, there's this bump. There's this increase in energy. This is my activation energy. This is the energy required to break the bonds between my reactant substances. And once they've achieved this much energy, they can form the product bonds and they can release the energy down and go down to here. On this one, we're looking at my reactants have a given amount of energy down here. My products have more energy, so they have to absorb energy. But I still can't just go from reactants to products. It doesn't work like that. We have to jump up higher. We have to meet this mark, which is the amount of energy needed to break these bonds. So my reactant bonds still have to be broken, and this gap here is the excess amount of energy that I need. Okay, so that's my activation energy, and then I can end up with this much energy in my products. So I still had to absorb some. In this case, you will feel the system or the surroundings get cold because the system is absorbing that energy. Okay, but those are endothermic and exothermic reactions. We talked about rate of reaction, which is change in concentration. It's affected by a couple different things. One of them is temperature. So as you increase the temperature, things move faster, reactions go quicker. 2, concentration reactants. If you have more reactants, they collide more and they react faster. And 3 is you add a catalyst. We're going to talk about catalysts just real quick. But you add a catalyst which will speed up a reaction. So again, the faster the rate of collisions, the faster the reaction will happen. So again, temperature speeds things up, they collide more. You add more stuff, it collides more. You add a catalyst, they collide more, they work faster. So a catalyst is something that speeds up a reaction because it lowers this activation energy. So without a catalyst, my reaction might need this much activation energy. With a catalyst, maybe I only need to get to here. Okay, and so this change in activation energy is what is causing your reaction to go faster. Important thing, your catalyst does not get changed in the reaction. It's not used, it doesn't affect anything, it just lowers the activation energy by giving a different means to the end, is how that works. All right, and we're going to look at chemical equilibrium today. So chemical equilibrium. We have, everything we've done thus far has always been, we have reactants go to products. Okay, but this isn't always the case. We don't always just have reactants go to products. Sometimes we have an incomplete or a reaction where not all the reactants are used up and not all the products are formed, or they go back and forth. So this is called a reversible reaction, when a reaction can go in both directions. So in this case, I have sulfur dioxide and oxygen gas form sulfur trioxide. So I can have 2 moles of sulfur dioxide react with 1 mole of oxygen to produce 2 moles of sulfur trioxide. Totally possible. I can also have my 2 moles of sulfur trioxide break down into 1 mole of oxygen and 2 moles of sulfur dioxide. And so this is all happening at the same time. What this reaction is looking for is chemical equilibrium. That is when the rate of the products returning to reactants will equal the forward reaction. So essentially you have reactants becoming products, and you have products becoming reactants, chemical equilibrium is when the rate of this and the rate of this are equal. Are equal. This is equilibrium. Your reactants becoming products is the same as your products becoming reactants. And we're going to look at this and how this kind of plays into things here. So there's a guy that looked into this. His name is Le Chatelier, and he had a principle. He had an idea that said the rates of the forward and reverse reactions will change to relieve the stress on the system. So this is an important principle. We're going to apply this. We're going to use this in different situations. So what we're looking at is a ratio. There's a ratio of reactants to products. And by changing this ratio, we can change the stress on the equilibrium, and we can change how it works. Okay? So for example, by adding product or removing reactant will force the reverse reaction. That will force this reaction. If I add product or I remove reactant, I'm going to force this reaction, the reverse reaction there. If I add reactants or remove products, I'm going to force the forward reaction. And so let's look at this in an actual scenario. Okay, so if we have, here's my ammonia reaction. I have nitrogen plus hydrogen produces ammonia and heat. Okay, so given this reaction here, given this situation, we know that this is an exothermic reaction because heat is on my product side. Okay, so I'm producing this and I'm giving off heat. All right, so now as I add nitrogen, I'm going to draw my reaction down here. And you can treat each one of these like their own separate component. So heat can be just like a substance. Okay, and I think of it this way. I'm gonna draw a big circle around my reaction. The part on top is the part that matters. The part on bottom just completes my circle. For example, if I add nitrogen, I'm going to come up from the bottom. I'm going to add nitrogen. This is going to force my reaction to go in this direction. And then I complete my circle. Okay, so this will affect the equilibrium by producing more products or pushing the forward reaction. So this is going to promote or encourage the forward reaction. If I add ammonia, if I add this guy, again, I'm adding here, I'm going to draw my circle, and I'm going to complete it on the bottom. The top part's what matters. So I added this. This is going to push the reverse reaction. Okay? If I lower the temperature, heat comes down. I complete my circle, which means I worry about the top part. I need more heat, so this is going to promote the forward reaction. And if I remove hydrogen, so H2 goes down, I complete my circle. It doesn't really matter which way you draw it to. It doesn't matter which one you go to, just to the other side of the arrow. And to complete the circle, I go this way, so this is going to be, again, the reverse reaction. We'll talk about this more in class. We'll do more practice with it, but that's how I think of it. That's how I kind of use this moving forward. Okay? So here are some review questions for you to work through. Make sure you pause this because I have another set on the next slide. So pause this, answer these questions, make sure you can work through these, and we will continue this discussion when you return to class. And here's your second set. So again, what's meant by a reversible reaction? And then here's your chance to practice. How does each of these affect your equilibrium? Which way is it going to promote? Forward reaction or reverse reaction is what I'm looking for here. All right, thank you very much. I wish you the best of luck, and I look forward to working with you through the rest of our gases and energy unit.